Look around you right now. Whatever you see, a city street, a forest, your bedroom. You're looking at the aftermath of the greatest massacre in the history of life on Earth. Every species you can name, every animal you've ever seen, every plant growing outside your window, they're all part of the 1%, the survivors, the lucky ones. If you're using these to fall asleep, that's literally why I make them. So, subscribe maybe, and tell me where are you and what time. 99% of every species that has ever existed on this planet is dead. Not just dead, extinct, gone forever. We're talking about billions of species that once crawled, flew, swam, and grew across every corner of Earth, now nothing but fossils, if we're lucky enough to find even those. You think you know about extinction. You've heard about the dinosaurs, maybe the dodo bird. But those are just the most recent chapters in a story of annihilation that has been playing out for nearly 4 billion years. A story where the house always wins, where survival is the exception, not the rule, and where every creature alive today exists only because their ancestors managed to dodge bullet after bullet in the most deadly game of chance imaginable. This isn't just about ancient history. This is about understanding why you exist at all. Because the fact that you're here, reading this, breathing, thinking, is statistically impossible. You are the descendant of an unbroken chain of survivors stretching back through countless mass extinctions, climate catastrophes, and evolutionary dead ends. Every one of your ancestors beat odds that make winning the lottery look like a sure thing. But here's what will really mess with your head. Right now, as you're listening to this, we're living through the 6th mass extinction in Earth's history. And for the first time, one species, us, is causing it. We are both the survivors of history's greatest killing spree and the architects of its latest chapter. The story begins 3.8 billion years ago, when the first primitive life forms appeared in Earth's ancient oceans. Simple bacterial cells, barely more complex than chemical reactions. But they had something that would define every living thing that came after them: the ability to make copies of themselves, to reproduce, to pass their genetic information to the next generation. For nearly 2 billion years, these microscopic organisms had the planet to themselves. They evolved slowly, developing new ways to capture energy, new chemical processes, new survival strategies. Some learned to harvest sunlight through photosynthesis. Others became predators, consuming their bacterial neighbors. Still others formed cooperative colonies, sharing resources and dividing labor. But even in this seemingly peaceful microbial world, extinction was already hard at work. Species evolved, flourished, then vanished as environmental conditions changed or better adapted competitors arose. The difference was scale. When a bacterial species went extinct, maybe a few thousand individuals died. The ocean was vast, and there was room for countless experiments in the game of life. Then everything changed. Around 2.5 billion years ago, something happened that would reshape the planet forever and trigger the first great dying. The organisms that had learned to photosynthesize, converting sunlight and carbon dioxide into energy, had a toxic side effect. They produced oxygen as waste. This might not sound like a catastrophe to you. After all, you need oxygen to breathe. But to most life on Earth at that time, oxygen was pure poison. The early atmosphere contained almost no free oxygen. Most organisms had evolved to live in what we would call an oxygen-free environment. They didn't just prefer it, they required it. Oxygen would literally burn through their cellular machinery, destroying them from the inside out. As photosynthetic bacteria multiplied across the oceans, they pumped more and more oxygen into the atmosphere. What started as a minor chemical imbalance became a global catastrophe. The oxygen levels rose slowly at first, then accelerated as vast bacterial mats spread across shallow seas and coastal waters. Within a few 100 million years, the atmosphere had been completely transformed. Scientists call this the Great Oxidation Event, but that's a sanitized name for what was actually the first mass extinction in Earth's history. As oxygen flooded the atmosphere and dissolved into the oceans, entire groups of organisms were wiped out. Species that had dominated the planet for over 1 billion years vanished in what, geologically speaking, was an instant. The anaerobic bacteria that had ruled the early Earth were suddenly living in a world that was toxic to them. They had two choices: adapt or die. Most chose poorly, not because they weren't trying to survive, but because evolution doesn't work that fast. You can't develop completely new cellular machinery in a few generations when your environment is actively killing you. But here's the twist that would define extinction patterns for the rest of Earth's history. The catastrophe that killed most existing species also created opportunities for new ones. The oxygen that was poison to anaerobic bacteria was fuel for a completely new kind of life. Organisms evolved that could not only tolerate oxygen, but use it to power more efficient cellular processes. These oxygen-breathing organisms had an enormous advantage. Aerobic respiration produces far more energy than anaerobic processes. They could grow faster, move quicker, and build more complex cellular structures. Within a few 100 million years, they had diversified into thousands of new species and occupied ecological niches that had never existed before. This pattern, catastrophe followed by rapid diversification, would repeat throughout Earth's history. Mass extinctions clear out existing species, then evolution rushes to fill the empty spaces with new experiments in survival. Each major dying creates opportunities for evolutionary innovation. But we're getting ahead of ourselves. For over 1 billion years after the Great Oxidation Event, life remained microscopic and relatively simple. Single cells, sometimes organized into colonies or primitive multicellular structures, but nothing you would recognize as an animal or plant. The real explosion was yet to come. Around 600 million years ago, something remarkable happened. Complex multicellular life appeared seemingly out of nowhere. Not just simple cell colonies, but organisms with specialized tissues, organs and body plans that looked almost modern. Scientists call this the Ediacaran period, named after the hills in Australia, where some of the first fossils were discovered. The Ediacaran organisms were unlike anything that had come before. Some looked like quilted discs lying on the sea floor. Others resembled feathers or ferns swaying in the current. Still others were bizarre, tube-like creatures that defied easy comparison to anything alive today. They had no shells, no hard parts, just soft bodies that somehow managed to preserve in the fossil record. For 40 million years, these strange organisms dominated the oceans. They were the first complex ecosystem, a community of species that interacted with each other and their environment in ways that simple bacteria never could. They developed the first predator-prey relationships, the first competition for resources, the first evolutionary arms races between species trying to eat each other and species trying to avoid being eaten. But their success was also their vulnerability. Complex organisms require stable environmental conditions. They need predictable food sources, consistent temperatures, appropriate chemical conditions in the water. When the environment changes rapidly, complex life faces a challenge that simple organisms can often avoid. There's more that can go wrong. Around 550 million years ago, the Ediacaran world began to fall apart. Climate shifted, ocean chemistry changed, and new kinds of organisms appeared that the old species couldn't compete with. Within a few million years, most Ediacaran species had vanished completely. Some may have evolved into other forms, but the vast majority simply died out, leaving behind only faint impressions in ancient rocks. Their disappearance set the stage for one of the most important events in the history of life, the Cambrian explosion. Starting around 540 million years ago, evolution went into overdrive. New body plans appeared faster than at any other time in Earth's history. Within 10 million years, which is practically instant in evolutionary terms, most of the major animal groups we recognize today had evolved. This was when animals first developed hard shells, exoskeletons, and internal skeletons. It was when eyes first appeared, along with claws, teeth, and sophisticated predatory behaviors. The Cambrian seas were full of experimental creatures that looked like nothing alive today. Opabinia, with its bizarre vacuum cleaner nose and 5 mushroom-shaped eyes. Hallucigenia, covered in spikes and walking on stilts. Anomalocaris, a 2-meter-long predator that ruled the seas like a prehistoric shark. But here's the thing about evolutionary explosions. They're followed by evolutionary crashes. Most of the weird and wonderful creatures that appeared during the Cambrian were experiments that failed. They represent evolutionary paths that seemed promising for a while, but ultimately led nowhere. By the end of the Cambrian, 490 million years ago, many of the most bizarre species had already gone extinct, replaced by more familiar-looking ancestors of modern animals. This boom and bust cycle would become the dominant pattern for the rest of Earth's history. Periods of rapid diversification, followed by mass extinctions, followed by new radiations of different species, each cycle eliminating most existing species while creating opportunities for new ones. The Ordovician period, which followed the Cambrian, saw the rise of the first complex marine ecosystems. Trilobites, those armored arthropods that would dominate the seas for 270 million years, reached their peak diversity. The first vertebrates appeared, primitive fish without jaws or bony skeletons. Corals built the first major reef systems, creating habitats that supported thousands of other species. For 45 million years, the Ordovician world seemed stable and prosperous. Ocean temperatures were warm, sea levels were high, and marine life flourished in shallow seas that covered much of what is now North America and Europe. It looked like life had finally found a sustainable pattern, a way to avoid the catastrophic collapses that had marked earlier eras. They were wrong. Around 450 million years ago, the second great mass extinction began. But this one was different from the oxygen catastrophe that had eliminated anaerobic bacteria. This was the first mass extinction caused by climate change, and it would establish a pattern that continues to this day. The trigger was ice. Lots of ice. For reasons that scientists still debate, Earth's climate suddenly shifted from warm and stable to cold and chaotic. Massive ice sheets formed at the South Pole, locking up so much water that sea levels dropped by over 100 meters. The warm, shallow seas that had supported most marine life drained away, leaving behind exposed continental shelves and drastically reduced ocean habitat. The temperature drop was catastrophic for species adapted to warm conditions. The ocean's circulation patterns that had carried nutrients around the globe were disrupted. Most devastating of all, the cold water held more oxygen than warm water, but in a way that made it unavailable to most marine animals. Species that had thrived in the oxygen-rich Ordovician seas found themselves suffocating in waters that should have been able to support them. The extinction unfolded in two phases. The first wave, triggered by the initial cooling and sea level drop, eliminated about 60% of all marine species. For a few million years, it looked like the survivors might recover. Some species began to adapt to the new conditions, and biodiversity started to increase again. Then came the second wave, even more devastating than the first. The ice sheets that had formed at the South Pole suddenly melted, possibly triggered by volcanic activity or changes in ocean circulation. Sea levels rose rapidly, reflooding the continental shelves. But the species that had adapted to the cold, low water conditions couldn't handle the sudden return to warm, high-water environments. By the time the Ordovician Silurian extinction was over, about 85% of all species on Earth were gone. Entire groups of organisms vanished completely. Most trilobite families disappeared, though some survivors would persist for hundreds of millions more years. The dominant predators of Ordovician seas, including massive nautiloid cephalopods, were reduced to a few small species. The reef ecosystems that had defined the period collapsed entirely. But in the aftermath of this catastrophe, something remarkable happened. The few surviving species found themselves in a world with abundant empty niches and reduced competition. Evolution responded with another burst of innovation. The Silurian period, which followed the extinction, saw the evolution of the first land plants, the first air-breathing arthropods, and the ancestors of all modern fish groups. Life on land, which had been limited to bacterial mats and simple fungi, suddenly became complex. Plants developed vascular systems that could transport water and nutrients, allowing them to grow much larger than their algal predecessors. Within 20 million years, the first forests appeared, creating entirely new terrestrial ecosystems. This was the beginning of a pattern that would repeat throughout Earth's history. Each mass extinction eliminated most existing species, but also removed the competition that prevented new evolutionary innovations. The survivors didn't just replace what had been lost, they evolved into forms that were more complex, more diverse, and often more resilient than their predecessors. The invasion of land by plants set off an evolutionary arms race that continues today. As plants spread across the continents, they created new opportunities for other organisms. The first land animals followed, initially small arthropods that fed on decaying plant matter. But within a few million years, predatory arthropods appeared, then the first vertebrates to leave the water. The late Devonian period, around 375 million years ago, was a time of incredible innovation in vertebrate evolution. The first amphibians evolved from fish, developing limbs that could support their weight on land while retaining the ability to breathe underwater. Forests spread across the continents, creating complex terrestrial food webs for the first time in Earth's history. In the oceans, fish diversified into forms that would be familiar today. The first sharks appeared, along with bony fish that would eventually give rise to most modern marine species. Reef ecosystems recovered from the Ordovician extinction and reached new levels of complexity. But success, as always in the history of life, was temporary. The late Devonian world, despite its apparent stability and diversity, was heading toward another catastrophe. This one would be different from the ice-driven Ordovician extinction, but no less devastating in its consequences. Around 375 million years ago, the first signs of trouble appeared in the fossil record. Reef systems began to collapse. Marine species started disappearing at accelerating rates. But this wasn't a sudden catastrophe triggered by climate change or volcanic activity. This was something new, a drawn-out crisis that unfolded over millions of years. The late Devonian extinction was actually a series of extinction pulses spread across nearly 20 million years. Each pulse eliminated different groups of organisms, creating a prolonged period of environmental stress and species loss. By the time it was over, about 75% of all species had vanished. The causes were complex and interconnected. The spread of forests on land had begun to alter the global climate in unexpected ways. Plants absorb carbon dioxide as they grow, and the rapid expansion of terrestrial vegetation removed vast amounts of CO2 from the atmosphere. This should have been good for preventing global warming, but it went too far. The cooling effect was so dramatic that it triggered another ice age, similar to the one that had caused the Ordovician extinction. At the same time, the new forests were affecting ocean chemistry. When plants die and decay, they consume oxygen. Rivers carrying organic matter from the new terrestrial ecosystems created dead zones in coastal waters where oxygen levels dropped to near zero. Fish and other marine animals that ventured into these areas suffocated. The reef ecosystems that had recovered from the Ordovician extinction were particularly vulnerable. Corals require warm, clear water with stable chemistry. The late Devonian world offered none of these things. Water temperatures fluctuated wildly as the climate shifted between ice age and greenhouse conditions. Ocean chemistry became increasingly acidic as organic matter from dying forests altered the pH of seawater. Most coral species couldn't adapt fast enough to survive these changes. But perhaps the most important aspect of the late Devonian extinction was what it revealed about the interconnectedness of life on Earth. This was the first mass extinction caused primarily by the success of life itself, rather than by external factors like volcanic eruptions or asteroid impacts. The evolution of forests, which seemed like an unqualified success story, had unintended consequences that rippled through the entire biosphere. This pattern, where evolutionary success in one group triggers environmental changes that cause extinctions in other groups, would become increasingly important as life became more complex and interconnected. It was a preview of the kind of extinction crisis that would eventually be triggered by another highly successful species: humans. The survivors of the late Devonian extinction found themselves in a world that had been fundamentally transformed. The reef ecosystems that had dominated marine environments for over 100 million years were gone, replaced by simpler communities of shellfish and early vertebrates. On land, the great forests had been reduced to scattered patches, creating opportunities for new kinds of plants and animals to evolve. One of the most important groups to benefit from this extinction was the early reptiles. During the Devonian, vertebrate life on land had been dominated by amphibians, which still required water for reproduction and were vulnerable to changes in climate and humidity. But in the aftermath of the extinction, some amphibian groups evolved new adaptations that made them less dependent on aquatic environments. The development of the amniotic egg was perhaps the most important innovation to emerge from the late Devonian crisis. Unlike amphibian eggs, which had to be laid in water, amniotic eggs contained their own water supply and could be laid on land. This gave reptiles access to terrestrial environments that amphibians couldn't exploit, and set the stage for the next great radiation of vertebrate life. The Carboniferous period that followed the late Devonian extinction was marked by the recovery and expansion of forest ecosystems, but these were different from the forests that had existed before. Instead of primitive vascular plants, the new forests were dominated by giant ferns, horsetails, and early gymnosperms. Some of these plants grew to enormous sizes. Tree ferns reached heights of 30 meters, creating dense canopies that blocked sunlight from reaching the forest floor. These carboniferous forests created the coal deposits that would later fuel the Industrial Revolution, but they also created new opportunities for animal evolution. The dense forests provided numerous ecological niches for arthropods, which reached sizes that seem impossible today. Dragonflies with wingspans of 70 centimeters patrolled the forest canopies. Millipedes grew to over 2 meters in length. Giant cockroaches scurried across the forest floor. The high oxygen levels in the carboniferous atmosphere, which reached 35% compared to today's 21%, allowed arthropods to grow much larger than they can today. Arthropods don't have lungs like vertebrates. They breathe through a system of tubes called tracheae. The efficiency of this system depends on the concentration of oxygen in the atmosphere. Higher oxygen levels meant that larger arthropods could still get enough oxygen to their tissues. But vertebrates were also diversifying rapidly during this period. Early reptiles split into multiple lineages, some of which would eventually lead to dinosaurs, mammals, and modern reptiles. The first reptiles to develop specialized diets appeared, including herbivores that could digest the tough plant material that made up the carboniferous forests. By the end of the Carboniferous, around 300 million years ago, Earth's ecosystems had recovered from the late Devonian extinction and reached new levels of complexity. Terrestrial food webs included multiple levels of predators and herbivores. Marine ecosystems had developed new kinds of reef systems based on different organisms than the coral reefs that had dominated earlier periods. It seemed like life had finally found a stable configuration, a way to maintain high diversity without triggering the environmental changes that had caused previous mass extinctions. The climate was warm and stable, atmospheric composition was favorable to both plant and animal life, and evolution seemed to be proceeding along predictable lines. Once again, they were wrong. Around 252 million years ago, the greatest catastrophe in the history of life was about to begin. An extinction so severe that it would earn the nickname the Great Dying. Unlike previous mass extinctions, which had eliminated 60 to 85% of species, this one would kill 96% of all marine species and 70% of all terrestrial vertebrates. It came closer to ending complex life on Earth than any other event in the past 600 million years. But that is a story for another time. For now, understand this. Every species alive today exists because their ancestors survived not just one or two mass extinctions, but multiple catastrophes that eliminated most life on Earth. The plants in your garden, the birds outside your window, the bacteria in your gut, they're all members of the 1% that made it through history's most deadly gauntlet. And the story is far from over. The patterns that drove extinction for nearly 4 billion years are still operating today. Environmental change, competition between species, the interconnected consequences of evolutionary success and failure, they're all still shaping which species survive and which disappear forever. You are living through the 6th mass extinction in Earth's history. Unlike the first 5, which were caused by volcanic eruptions, climate change, and asteroid impacts, this one has a single cause: the success of one species. US humans have become the most successful large animals in Earth's history. And our success is triggering environmental changes that rival the great catastrophes of the geological past. The question isn't whether this extinction will happen. It's already happening. Species are disappearing at rates not seen since the asteroid that killed the dinosaurs. The question is whether humans, the architects of this crisis, will also become its victims, or whether we'll join the exclusive club of species that have survived multiple mass extinctions. We are the descendants of survivors, but we're also the inheritors of a planet where survival is never guaranteed, where success often carries the seeds of its own destruction, and where 99% of everything that has ever lived has already lost the ultimate game of chance. The story of extinction is the story of life itself, and that story is still being written. 252 million years ago, Earth experienced something so catastrophic that scientists struggle to find words for it. They call it the Great Dying, but that sanitized name doesn't capture the sheer scope of what happened. This wasn't just another mass extinction. This was the closest life on Earth has ever come to complete annihilation. Imagine every single species you know, every bird, every fish, every insect, every plant. Now imagine 96% of them dead, gone forever. The oceans turned into toxic wastelands where almost nothing could survive. The land became a hellscape of acid rain, poisonous gases, and temperatures that killed most living things. For millions of years, Earth looked like an alien world where complex life seemed impossible. The Permian-Triassic extinction didn't just kill individual animals and plants, it destroyed entire ecosystems, collapsed food webs that had existed for hundreds of millions of years, and eliminated evolutionary lineages that had survived every previous catastrophe. It was so severe that it took 10 million years for biodiversity to recover to pre-extinction levels. 10 million years. That's longer than humans have existed as a species. But here's what makes this extinction truly terrifying from our modern perspective. It was caused by the same thing that's driving the current extinction crisis: rapid climate change triggered by massive releases of greenhouse gases into the atmosphere. The Great Dying is a preview of what happens when the planet's climate system breaks down completely. The story begins in what is now Siberia, 252 million years ago. Deep beneath the Earth's surface, something was building pressure. Not a single volcano, but an entire system of volcanic activity covering an area larger than the continental United States. The Siberian traps, as geologists call them today, were preparing to unleash the largest volcanic eruption in the planet's history. When the eruption began, it didn't stop. For over 1 million years, massive amounts of lava poured across the Siberian landscape, creating layers of volcanic rock over 1 kilometer thick. The lava flows alone would have been devastating to local ecosystems, but they were just the beginning. The real killer was what came out of the volcanoes along with the lava: massive quantities of greenhouse gases, carbon dioxide, methane, sulfur compounds, and other toxic chemicals. These gases didn't just affect the immediate area around the volcanoes. They spread through the atmosphere and oceans, altering the chemistry of the entire planet. The carbon dioxide caused rapid global warming. Temperatures rose by 8 to 10 degrees Celsius, turning much of the planet into a hothouse where most species couldn't survive. But the warming was just the first phase of the catastrophe. As temperatures rose, they triggered a cascade of secondary effects that made the crisis exponentially worse. Warmer oceans released dissolved methane from seafloor deposits, adding even more greenhouse gases to the atmosphere. The heating accelerated chemical weathering of rocks on land, which consumed oxygen and released more carbon dioxide. Most devastating of all, the warming oceans began to lose their ability to hold dissolved oxygen. In the deep ocean, where cold water had previously carried oxygen to the sea floor, circulation patterns broke down. Vast areas of the ocean became anoxic, completely devoid of oxygen. In these dead zones, bacteria that didn't need oxygen took over, producing hydrogen sulfide as a waste product. Hydrogen sulfide is toxic to most life forms, and in high concentrations, it's deadly. As the anoxic zones expanded, they began producing so much hydrogen sulfide that it started bubbling up to the surface and escaping into the atmosphere. The oceans were literally producing poison gas. On land, the situation was equally dire. The massive volcanic eruptions had injected sulfur compounds into the atmosphere, which combined with water vapor to produce acid rain. This wasn't the relatively mild acid rain caused by modern industrial pollution. This was concentrated sulfuric acid falling from the sky, capable of dissolving flesh and plant tissue on contact. The acid rain killed vegetation across vast areas, eliminating the base of terrestrial food webs. Without plants, herbivorous animals starved. Without herbivores, carnivores followed. The complex ecosystems that had developed during the Permian period collapsed in what may have been just a few thousand years. But the crisis went deeper than just killing existing species. The environmental changes were so severe that they prevented new species from evolving to replace the extinct ones. The normal process of evolution, where environmental pressure leads to adaptation and diversification, couldn't function when the environment itself was toxic to most forms of life. In the oceans, the combination of high temperatures, low oxygen, toxic hydrogen sulfide, and acidic conditions created what scientists call a kill mechanism that eliminated species faster than evolution could replace them. Marine ecosystems that had flourished for hundreds of millions of years were reduced to simple communities of bacteria and a few highly specialized organisms that could tolerate extreme conditions. The reef ecosystems that had recovered from previous extinctions were completely destroyed, not just damaged or reduced, but eliminated entirely. For millions of years after the Great Dying, there were no coral reefs anywhere on Earth. The ecological niches that reefs had provided for thousands of species simply ceased to exist. On land, forests that had dominated terrestrial environments since the Carboniferous period were reduced to scattered patches of the most hardy species. Vast areas that had been covered by diverse plant communities became barren wastelands where only the most primitive plants could survive. The fossil record from this period tells a story of almost complete ecological collapse. In many locations, the rock layers deposited during the extinction contain almost no fossils at all. Life didn't just become rare. In many environments, it virtually disappeared entirely. The few species that managed to survive the Great Dying had several characteristics in common. They were small, which reduced their energy requirements and made them less vulnerable to food web collapse. They were generalists, capable of eating a wide variety of foods when their preferred diet became unavailable. Most importantly, they could tolerate extreme environmental conditions that would kill more specialized species. Among the survivors were the ancestors of dinosaurs. The archosaurs, reptilian predators that had been relatively minor players in Permian ecosystems, found themselves in a world where most of their competitors had been eliminated. Small, agile, and adaptable, they were perfectly positioned to take advantage of the empty ecological niches left by the extinction. Another group of survivors were the early mammals, or rather, the mammal-like reptiles called therapsids that would eventually give rise to true mammals. These animals had already evolved some of the physiological features that would make mammals successful: efficient metabolisms, better temperature regulation, and more complex social behaviors than typical reptiles. But survival during the Great Dying wasn't just about having the right biological features. It was also about luck. Even well-adapted species could be wiped out by local catastrophes, volcanic eruptions, toxic gas releases, or simply the randomness of environmental collapse. The difference between extinction and survival often came down to whether a population happened to be in the right place at the right time. The recovery from the Great Dying was unlike anything that had followed previous mass extinctions. Instead of rapid diversification, as surviving species filled empty niches, there was a prolonged period of what scientists call the dead zone. For nearly 5 million years after the main extinction event, biodiversity remained extremely low. Evolution seemed almost frozen. Part of the problem was that the environmental conditions that had caused the extinction persisted long after the volcanic eruptions ended. High temperatures, toxic oceans, and unstable climate continued to prevent most attempts at evolutionary innovation. Species that tried to become larger or more specialized were quickly eliminated by recurring environmental crises. But gradually, very gradually, conditions began to improve. The volcanic activity in Siberia finally stopped. The excess greenhouse gases in the atmosphere were slowly absorbed by rock weathering and ocean chemistry. Oxygen levels in the oceans began to rise as circulation patterns were re-established. Around 247 million years ago, about 5 million years after the worst of the extinction, life began to diversify again. This was the beginning of the Triassic period, and it would see one of the most dramatic evolutionary radiations in Earth's history. The empty world left by the Great Dying created opportunities for evolutionary experiments that would have been impossible when competition was intense. The archosaurs that had survived as small, generalized predators began to diversify into forms that filled every conceivable ecological niche. Some became large predators, evolving the body plans and hunting strategies that would later characterize dinosaurs. Others became herbivores, developing new ways to digest plant material and growing to sizes that allowed them to reach vegetation that smaller animals couldn't access. Still others took to the water, evolving into marine reptiles that would dominate ocean ecosystems for the next 150 million years. The Triassic radiation wasn't just about archosaurs. Surviving plant groups also diversified rapidly, developing new forms that were better adapted to the changed climate conditions. The first conifers appeared during this period, with needle-like leaves that reduced water loss and allowed them to survive in drier conditions than their predecessors. In the oceans, new kinds of reef-building organisms evolved to replace the extinct coral communities. These weren't true corals as we know them today, but various kinds of sponges, algae, and other organisms that could create similar ecological structures. Marine reptiles radiated into forms that paralleled the diversity of modern marine mammals, including dolphin-like ichthyosaurs and whale-like plesiosaurs. But the most important evolutionary development of the Triassic period was the origin of the dinosaurs themselves. Around 230 million years ago, some archosaur lineages evolved the upright posture, efficient metabolism, and sophisticated behavioral patterns that would make dinosaurs the dominant land animals for the next 165 million years. Early dinosaurs were small, bipedal predators that looked more like large lizards than the giants we typically think of. But they had several key advantages over other reptiles of their time. Their upright posture made them faster and more maneuverable. Their metabolism was more efficient, allowing them to maintain higher activity levels. Most importantly, many species showed evidence of complex social behaviors, including parental care and cooperative hunting. Within 20 million years of their first appearance, dinosaurs had diversified into multiple ecological roles. Some remained small predators, but others evolved into large herbivores, armored defensive specialists, and massive carnivores that could take down prey much larger than themselves. The success of dinosaurs during the Triassic wasn't just due to their superior adaptations. It was also because they were evolving in a world that was still recovering from the Great Dying. Competition was reduced, resources were abundant, and environmental conditions were relatively stable compared to the chaos of the Extinction period. By the end of the Triassic, around 200 million years ago, Earth's ecosystems had not only recovered from the Great Dying, but had reached new levels of complexity and diversity. Dinosaur-dominated terrestrial communities included multiple levels of predators and herbivores. Marine ecosystems supported diverse communities of reptiles, fish, and invertebrates. Plant communities had evolved new strategies for dealing with herbivorous dinosaurs, including the first evidence of grasses and flowering plants. But this recovery came with a hidden vulnerability. The ecosystems that had evolved after the Great Dying were highly dependent on stable climate conditions. The dinosaurs and other dominant groups had evolved during a period of relatively warm, stable temperatures. Their physiology and behavior were optimized for these conditions. When climate stability ended, as it inevitably did, these specialized ecosystems would prove to be vulnerable in ways that the more generalized communities of earlier periods had not been. The late Triassic extinction, around 200 million years ago, was smaller than the Great Dying, but still eliminated about 75% of species. This extinction was also caused by massive volcanic eruptions, this time associated with the breakup of the supercontinent Pangaea. The pattern was becoming clear. Major volcanic events could trigger cascade effects that led to mass extinction. But the late Triassic extinction also demonstrated something new about the evolution of complex ecosystems. The species that survived weren't necessarily the most generalized or hardy. Instead, some highly specialized groups, including the dinosaurs, not only survived, but expanded their dominance after the extinction. This suggested that evolution was entering a new phase, where specialization and ecological complexity could sometimes be advantages during mass extinctions, rather than just disadvantages. The dinosaurs that survived the late Triassic extinction were those with the most advanced physiological and behavioral adaptations, not the most primitive or generalized forms. The Jurassic period that followed, from 200 to 145 million years ago, was the golden age of dinosaur evolution. This was when the giant sauropods evolved, creatures like Brontosaurus and Diplodocus that reached lengths of over 30 meters and weights of 50 tons or more. It was also when the first giant predators appeared, including Allosaurus and other massive carnivores that could hunt even the largest herbivores. But the Jurassic also saw important developments in other groups. The first birds evolved from small predatory dinosaurs, developing powered flight and beginning the conquest of aerial environments. In the oceans, marine reptiles reached their peak diversity, with some ichthyosaurs growing larger than modern blue whales. Plant evolution also accelerated during the Jurassic. The first flowering plants appeared, bringing new efficiency to plant reproduction and creating new opportunities for animal-plant interactions. The co-evolution of flowering plants and insects began during this period, leading to the incredible diversity of both groups that characterizes modern ecosystems. By the middle of the Jurassic, Earth's biodiversity had reached levels that exceeded anything seen before the Great Dying. But this diversity came with a cost: increased specialization and interdependence that made ecosystems more vulnerable to disruption. The Cretaceous period, from 145 to 66 million years ago, saw this trend toward specialization reach its peak. Dinosaurs diversified into forms that filled every conceivable ecological niche. Some developed elaborate display structures like the frills of Triceratops or the crests of Parasaurolophus. Others, like Tyrannosaurus rex, became highly specialized predators with adaptations for hunting specific types of prey. Flowering plants underwent their own radiation during the Cretaceous, diversifying into most of the major groups we recognize today. Forests became dominated by angiosperms rather than conifers, creating new kinds of habitats and food webs. The coevolution of plants and insects reached new levels of sophistication, with some species becoming completely dependent on each other for survival. Marine ecosystems also reached new levels of complexity. The oceans were dominated by marine reptiles that had no modern equivalents, including massive predators like Mosasaurus and long-necked plesiosaurs that could reach lengths of 15 meters. Coral reefs returned and became more diverse than they had been before the Great Dying. For over 80 million years, the Cretaceous world seemed stable and prosperous. Dinosaurs had proven their evolutionary success by surviving multiple minor extinction events and adapting to gradual climate changes. They had colonized every continent and diversified into forms adapted to every major terrestrial habitat. The idea that such successful, long-lived and diverse groups could be completely eliminated seemed impossible. Dinosaurs had survived for over 150 million years, far longer than any mammalian group has existed. They had weathered climate changes, volcanic eruptions, and competition from other groups. They seemed to be one of evolution's permanent success stories. But 66 million years ago, something happened that changed everything. Not gradually, like the volcanic eruptions that had caused previous mass extinctions, but instantaneously in geological terms. A 10-kilometer-wide asteroid slammed into Earth at a speed of 20 kilometers per second, releasing energy equivalent to billions of nuclear bombs. The impact site was in what is now Mexico's Yucatan Peninsula, but the effects were global and immediate. The collision vaporized the asteroid and excavated a crater 180 kilometers wide. Rock and debris were blasted into the atmosphere with such force that some material achieved escape velocity and left Earth entirely. But most of it fell back down as a rain of superheated particles that ignited fires across the planet. Within hours, the entire Earth was engulfed in flames. The heat from falling debris was so intense that it could ignite plant material just by radiation, without direct contact. Forests that had existed for millions of years burned to ash in a single day. Animals that couldn't find shelter underground or underwater were cooked alive. But the fires were just the beginning. The impact had vaporized sulfur-rich rocks at the impact site, releasing massive amounts of sulfur compounds into the atmosphere. These compounds combined with water vapor to produce acid rain far more severe than anything during the Great Dying. The acid rain continued for months, poisoning surviving vegetation and making surface water toxic to most life forms. Even worse was the dust and debris thrown into the upper atmosphere. So much material was ejected that it blocked sunlight from reaching the Earth's surface. For months, possibly years, the planet was shrouded in darkness. Temperatures dropped rapidly as the sun's energy could no longer warm the surface. The impact winter that followed was more severe than any ice age in Earth's history. Photosynthesis stopped. Plants that survived the initial fires and acid rain began dying from lack of light. Without photosynthesis, atmospheric oxygen levels began to drop. The entire base of Earth's food webs collapsed within a matter of months. Large animals were the first to die. Dinosaurs, which had dominated terrestrial ecosystems for over 150 million years, were eliminated within a few thousand years of the impact. Their large size, which had been an advantage during normal times, became a liability when food became scarce. They simply couldn't find enough to eat in the post-impact wasteland. Marine ecosystems collapsed even more completely than terrestrial ones. The darkness stopped oceanic photosynthesis, eliminating the phytoplankton that formed the base of marine food webs. Without phytoplankton, the entire oceanic ecosystem, from the smallest fish to the largest marine reptiles, began to starve. The ammonites, nautilus-like creatures that had dominated marine environments for over 300 million years, went completely extinct. But unlike the Great Dying, which had eliminated species gradually over hundreds of thousands of years, the asteroid impact created conditions that favored certain types of survivors. Small size was crucial, as it reduced energy requirements when food was scarce. Generalized diets were essential for species that could no longer rely on their preferred foods. Most importantly, the ability to enter dormancy, either through hibernation, estivation, or seed formation, allowed some species to wait out the worst conditions. Among the survivors were small mammals, which had remained relatively small and generalized throughout the age of dinosaurs. Birds, which were actually dinosaurs themselves but had evolved flight, and many species had small body sizes. Crocodiles and turtles, which could survive long periods without food. Many plants survived as seeds, which could remain dormant for years before germinating when conditions improved. The Cretaceous-Paleogene extinction eliminated about 75% of all species, but unlike previous mass extinctions, it was highly selective. It specifically eliminated large animals while allowing many smaller species to survive. This created a very different kind of post-extinction world than had followed earlier catastrophes. The Paleogene period that followed, beginning 66 million years ago, saw rapid diversification among the surviving groups. Without competition from dinosaurs, mammals quickly radiated into forms that filled the vacant ecological niches. Within 10 million years, mammals had evolved from small, shrew-like creatures into forms as diverse as whales, bats, and early primates. This mammalian radiation was faster and more dramatic than anything seen in previous post-extinction recoveries. Part of this was due to mammals' physiological advantages. Warm-bloodedness, efficient metabolism, and complex parental care allowed them to exploit resources and environments that cold-blooded reptiles couldn't access as effectively. But the rapid pace of mammalian evolution also reflected something new about the post-extinction environment. The asteroid impact had not just eliminated dinosaurs, it had also triggered climate and environmental changes that created new opportunities for evolutionary innovation. The flowering plants that had co-evolved with dinosaurs during the Cretaceous suddenly found themselves without their primary herbivores. This released them from evolutionary pressures that had shaped their development for tens of millions of years. Plants began evolving new forms and strategies, including the grasses that would eventually create the world's major grassland ecosystems. The coevolution of mammals and flowering plants became one of the defining features of post-extinction ecosystems. Unlike the reptile-plant interactions that had characterized earlier periods, mammal-plant relationships were often more dynamic and complex. Mammals could disperse seeds over greater distances, pollinate flowers more efficiently, and create new kinds of disturbance patterns that promoted plant diversity. By 50 million years ago, the world had been completely transformed from the dinosaur-dominated ecosystems of the Cretaceous. Mammals had diversified into most of the major groups we recognize today. Grasslands had appeared and begun spreading across the continents. The first kelp forests had evolved in the oceans. Even the climate had shifted to new patterns that were driven more by ocean circulation than by the atmospheric chemistry that had dominated earlier periods. But the Paleogene world, despite its rapid diversification and apparent success, was built on the same fundamental vulnerability that had characterized all previous post-extinction ecosystems. The species that evolved after the asteroid impact were adapted to the specific environmental conditions that existed during the recovery period. When those conditions changed, as they inevitably would, these specialized ecosystems would face their own extinction crises. The pattern was becoming clear across 200 million years of mass extinctions and recoveries. Each major catastrophe eliminated most existing species, but created opportunities for evolutionary innovation. The survivors weren't necessarily the best adapted species in any absolute sense, but rather those that happened to have characteristics that helped them survive the specific crisis they faced. More importantly, each post-extinction radiation produced ecosystems that were more complex and specialized than their predecessors. The simple communities that survived mass extinctions evolved into intricate networks of interdependent species. These complex ecosystems were capable of supporting higher biodiversity and more efficient energy use than simpler communities, but they were also more vulnerable to disruption. The story of extinction wasn't just about death and catastrophe. It was about the creative power of evolutionary crisis. Every mass extinction had opened new possibilities for life, allowing evolution to explore directions that would have been impossible when competition was intense and ecological niches were already filled. But creativity came with a cost. Each round of extinction and recovery had produced species that were more specialized, ecosystems that were more complex, and evolutionary lineages that were more vulnerable to the next inevitable catastrophe. By the end of the Paleogene, 34 million years ago, this pattern had reached a new level of sophistication. The mammal-dominated world that had emerged from the asteroid impact was more diverse, more complex, and more interconnected than any ecosystem in Earth's history. But it was also more fragile, more dependent on stable conditions, and more vulnerable to the kinds of rapid environmental change that had triggered every previous mass extinction. The stage was set for the next great test of life's resilience, and this time, the agent of change would be unlike any that had come before. 34 million years ago, Earth entered a new phase of its extinction story. For the first time in the planet's history, the next great dying wouldn't be caused by volcanic eruptions, asteroid impacts, or sudden atmospheric changes. Instead, it would be driven by something that seemed impossible: ice. The transition from the warm Paleogene world to the Ice Age cycles of the Quaternary represents more than just climate change. It marks the beginning of extinction, driven by planetary cooling, orbital mechanics, and ultimately the emergence of a species so successful that it would become the primary driver of extinction for the first time in Earth's 4 billion-year history. But we're getting ahead of ourselves. First came the ice. The Oligocene epoch, beginning 34 million years ago, marked the start of a dramatic global cooling trend that continues today. The warm, stable climate that had allowed mammals to diversify after the asteroid impact began to deteriorate. Ocean temperatures dropped, atmospheric CO2 levels fell, and for the first time in over 100 million years, ice sheets began forming at the poles. This cooling wasn't caused by any single catastrophic event. Instead, it was the result of gradual changes in ocean circulation, atmospheric chemistry, and the positions of the continents. As continents drifted toward their modern positions, they altered patterns of ocean currents and wind circulation. The formation of the Drake Passage between South America and Antarctica allowed cold circumpolar currents to form, isolating Antarctica from warm tropical waters. At the same time, the rise of the Tibetan Plateau and the Himalayas, caused by the collision between India and Asia, created new patterns of atmospheric circulation that affected global weather patterns. These mountain ranges acted like giant walls that redirected air masses and altered the distribution of precipitation across Asia and beyond. The cooling had profound effects on global ecosystems. Tropical forests, which had covered much of the planet during the warm Paleogene, began retreating toward the equator. In their place, new types of vegetation evolved that were adapted to cooler, drier conditions. Grasslands expanded dramatically, creating vast savannas that supported new kinds of herbivorous mammals. This transition from forest to grassland triggered one of the most important evolutionary radiations of the Cenozoic era. Large herbivorous mammals evolved to take advantage of the abundant grass, developing new digestive systems that could process cellulose efficiently. Horses, camels, elephants, and many other groups underwent major evolutionary changes during this period, becoming larger and more specialized for life in open environments. But specialization came with vulnerability. As mammals became adapted to specific climatic conditions and food sources, they became more susceptible to environmental change. When climate fluctuations intensified during the later Cenozoic, many highly specialized species would be eliminated by relatively minor environmental shifts. The Miocene epoch, from 23 to 5 million years ago, saw this pattern of specialization and vulnerability play out on a global scale. This was the peak of mammalian diversity, with more species of mammals than at any other time in Earth's history. But it was also the beginning of a long-term decline in mammalian diversity that continues today. The Miocene world was dramatically different from anything we know today. Forests extended much farther north than they do now, supporting diverse communities of primates, including the ancestors of humans, across Europe and Asia. The Mediterranean Sea periodically dried up completely, creating land bridges between Africa and Europe that allowed massive migrations of mammals between continents. But the most important development of the Miocene was the continued expansion of grasslands and the evolution of grazing ecosystems. The coevolution of grasses and large herbivores created some of the most productive ecosystems in Earth's history. Vast herds of horses, camels, rhinoceroses, and early elephants moved across continents in migrations that rivaled anything in the modern world. These Miocene ecosystems supported predator-prey relationships of incredible complexity. Giant cats like Amphimacheirodus hunted prey larger than modern elephants. Packs of bone-crushing dogs pursued herds of horses across ancient grasslands. In the oceans, the first true baleen whales evolved to exploit the rich plankton communities supported by global ocean circulation patterns. But this diversity and productivity was built on climate stability that couldn't last forever. Around 15 million years ago, the first signs of the coming Ice Age crisis began to appear in the fossil record. Species adapted to warm conditions started going extinct at accelerating rates, while cold-adapted species began expanding their ranges. The transition was gradual at first. Individual species disappeared, new ones evolved to replace them, and ecosystems slowly shifted toward forms better adapted to cooler conditions. But around 3 million years ago, the pace of change accelerated dramatically. This was when Earth's climate entered the Quaternary Ice Age cycle, a pattern of glacial and interglacial periods that would dominate the next 3 million years. Unlike the gradual cooling of earlier periods, the Quaternary was characterized by rapid oscillations between ice age and temperate conditions, driven by periodic changes in Earth's orbit around the Sun. These orbital cycles, known as Milankovitch cycles, occur on timescales of 20,000 to 100,000 years. As Earth's orbital eccentricity, axial tilt, and precession change, they alter the amount and distribution of solar energy reaching the planet's surface. When orbital conditions favor cooling, ice sheets grow rapidly across northern continents. When they favor warming, the ice sheets melt just as quickly. For species adapted to stable conditions, these rapid climate oscillations were catastrophic. Every 20,000 to 100,000 years, entire ecosystems had to shift hundreds or thousands of kilometers as ice sheets advanced and retreated. Species that couldn't migrate fast enough went extinct. Those that survived had to repeatedly adapt to completely different environmental conditions. The Quaternary extinctions were different from previous mass extinctions in several important ways. They were ongoing, with species disappearing throughout the period rather than in discrete events. They were selective, primarily affecting large animals while leaving smaller species relatively unaffected. Most importantly, they accelerated over time, with extinction rates increasing as the Ice Age cycles continued. The first major wave of Quaternary extinctions began around 2.5 million years ago and primarily affected large marine mammals. The cooling oceans and changing circulation patterns eliminated many species of whales, seals, and marine reptiles that had evolved during the warmer Miocene. Entire groups, like the desmostylians, bizarre marine mammals that had no modern equivalents, disappeared completely. On land, the pattern was more complex. Some large mammals went extinct as their preferred habitats shifted or disappeared, but others, particularly those adapted to cold conditions, actually diversified during glacial periods. Mammoths, woolly rhinoceroses, cave bears, and giant deer evolved during the ice ages and reached their peak diversity when ice sheets covered much of northern Europe and North America. But the most important development during the Quaternary wasn't the extinction of existing species. It was the evolution of a new kind of primate in Africa, one whose descendants would eventually become the most successful large mammals in Earth's history, and eventually the primary cause of extinction for thousands of other species. The human lineage split from our closest relatives, the ancestors of chimpanzees and bonobos, around 7 million years ago in Africa. For most of their evolutionary history, early humans were just another species of large primate, neither particularly numerous nor ecologically significant. They lived in small groups, used simple tools, and had little impact on their environments. But around 2.5 million years ago, the same time that Quaternary extinctions were accelerating, something changed in human evolution. Early humans began making more sophisticated tools, hunting larger prey, and showing evidence of complex social behaviors. This was the beginning of a feedback loop between cultural innovation and biological evolution that would eventually make humans unlike any species in Earth's history. The key difference was that humans evolved the ability to accumulate cultural knowledge across generations. While other species had to rely entirely on genetic adaptation to environmental change, humans could develop new technologies, strategies, and social structures much faster than biological evolution could operate. This gave them an enormous advantage in dealing with the rapidly changing conditions of the Ice Age world. As glacial cycles intensified around 1 million years ago, human populations were repeatedly forced to adapt to new environments. Each climate shift eliminated some human groups, but also created selective pressure for those who survived to become more adaptable, more innovative, and better at cooperating in large groups. The genetic bottleneck we discussed earlier, when human populations were reduced to around 1,280 individuals 900,000 years ago, was part of this process. The survivors weren't just lucky, they were the descendants of populations that had already been selected for adaptability, intelligence, and social cooperation by hundreds of thousands of years of climate instability. By 500,000 years ago, humans had spread across Africa and into Europe and Asia. Different populations evolved distinct adaptations to their local environments, but all retained the fundamental human characteristics: large brains, sophisticated tool use, complex social structures, and the ability to transmit cultural knowledge. The Neanderthals who evolved in Europe were perfectly adapted to Ice Age conditions. The Denisovans in Asia developed genetic adaptations to high altitudes and possibly marine environments. The ancestors of modern humans in Africa continued to refine the technological and social innovations that had allowed them to survive the earlier bottleneck. For hundreds of thousands of years, these human populations had relatively little impact on other species. They were skilled hunters, but their populations were small and their technology was limited. They caused local extinctions of some large mammals, but nothing approaching the scale of natural climate-driven extinction. But around 70,000 years ago, something fundamental changed in human evolution. Archaeological evidence suggests that this was when humans developed fully modern cognitive abilities: abstract thinking, symbolic communication, artistic expression, and the ability to plan complex activities far in advance. This cognitive revolution transformed humans from just another large mammal into something unprecedented in Earth's history: a species capable of intentionally modifying environments on a large scale. Within a few thousand years, humans were using fire to manage landscapes, driving species extinctions through overhunting, and beginning to domesticate other species for their own purposes. The first clear evidence of human-caused extinctions appears around 50,000 years ago, when modern humans reached Australia. Within a few thousand years of human arrival, most of Australia's large mammals were extinct. Giant kangaroos, marsupial lions, massive wombats, and flightless birds that had survived millions of years of climate change disappeared shortly after humans developed the technology to hunt them effectively. The pattern repeated as humans spread to other continents. When humans reached the Americas around 15,000 years ago, they encountered ecosystems full of large mammals that had never seen human hunters: mammoths, mastodons, giant ground sloths, saber-toothed cats, and many others. Within 2,000 years, most of these species were extinct. This wasn't just coincidence. The timing of human arrival and megafaunal extinction is too consistent across continents to be explained by climate change alone. Moreover, the extinctions were highly selective, primarily affecting large mammals, while leaving smaller species largely unaffected. This is exactly the pattern expected from human hunting pressure. But human-caused extinction accelerated dramatically around 10,000 years ago with the development of agriculture. The domestication of plants and animals allowed human populations to grow far beyond what hunting and gathering could support. Larger populations required more land, more resources, and had greater environmental impacts. Agriculture also fundamentally changed humanity's relationship with other species. Instead of adapting to existing ecosystems, humans began creating simplified ecosystems designed to maximize the production of desired species. Forests were cleared for farmland, wetlands were drained, and wild animals were eliminated as agricultural pests or competitors. The rise of agricultural civilizations over the past 10,000 years has been accompanied by waves of extinction that dwarf anything in the previous history of human-caused species loss. Each expansion of agricultural societies eliminated native species and ecosystems that had existed for millions of years. But the real acceleration began just 500 years ago, when global trade networks allowed humans to transport species around the world and European colonization spread agricultural practices to every continent. Island ecosystems, which had evolved in isolation for millions of years, were particularly vulnerable to introduced species and habitat destruction. The dodo, which became extinct in 1662, is just one example of thousands of island species eliminated by human activities. The passenger pigeon, which may have been the most numerous bird species in North America, was driven to extinction by commercial hunting in 1914. The thylacine, Australia's largest predator, was hunted to extinction in 1936. Each of these extinctions represented the end of evolutionary lineages that had persisted for millions of years. The dodo was the only flightless bird in the Indian Ocean. The passenger pigeon played a crucial role in North American forest ecosystems. The thylacine was the largest carnivorous marsupial in the world. When they disappeared, they took with them genetic information and ecological functions that had been millions of years in the making. But individual extinctions, dramatic as they were, pale in comparison to what has happened over the past 200 years. The Industrial Revolution marked the beginning of human impacts on a truly global scale. Fossil fuel combustion began altering atmospheric chemistry. Industrial processes released toxic chemicals into air and water. Urban and industrial development consumed natural habitats at unprecedented rates. Most importantly, human populations began growing exponentially. In 1800, there were about 1 billion humans on Earth. By 1900, there were 1.6 billion. By 2000, there were 6 billion. Today, there are over 8 billion, and the population continues to grow. Each human requires resources: food, water, energy, materials for shelter, and clothing. These resources come from natural ecosystems, and extracting them inevitably affects other species. As human populations have grown, the total impact on Earth's ecosystems has reached levels that rival the great catastrophes of the geological past. Modern extinction rates are now estimated to be 100 to 1,000 times higher than natural background rates. This puts the current crisis in the same category as the asteroid impact that killed the dinosaurs or the volcanic eruptions that caused the Great Dying. But unlike those events, which were caused by external forces, the current extinction is being driven by the deliberate activities of a single species. Climate change caused by human greenhouse gas emissions is altering global weather patterns, ocean chemistry, and temperature distributions. Many species adapted to specific climate conditions are being eliminated as their preferred environments disappear. Ocean acidification, caused by absorbed CO2, is dissolving the shells of marine organisms and disrupting marine food webs. Habitat destruction for agriculture, urban development, and resource extraction has eliminated or fragmented most of Earth's natural ecosystems. Species that require large territories or specific habitat conditions are particularly vulnerable. Many large mammals, birds of prey, and forest-dependent species have been reduced to small, isolated populations that are vulnerable to local extinction. Pollution from industrial activities, agriculture, and urban areas has contaminated air, water, and soil across the planet. Chemical pollutants can kill species directly or disrupt their reproduction, development, or behavior. Plastic pollution in the oceans is affecting marine life from the smallest plankton to the largest whales. The introduction of invasive species, either deliberately or accidentally, has disrupted ecosystems that evolved in isolation for millions of years. Island ecosystems have been particularly affected, with introduced predators, competitors, and diseases causing waves of extinction among native species. Perhaps most significantly, humans are now consuming biological resources faster than natural systems can regenerate them. Overfishing has collapsed marine ecosystems that supported complex food webs for millions of years. Deforestation is eliminating forests faster than they can regrow. Overhunting and poaching continue to drive species toward extinction for commercial purposes. The cumulative effect of all these impacts is an extinction crisis that matches or exceeds the great mass extinctions of the geological past. Species are disappearing at rates not seen since the asteroid impact 66 million years ago. But unlike previous mass extinctions, which eliminated species more or less randomly, the current crisis is highly selective. Large animals are disappearing first, just as they did during the Ice Age extinctions, but at a much faster pace. Species with limited geographic ranges are more vulnerable than widespread species. Animals and plants that require specific habitat conditions are more threatened than generalists. Species that reproduce slowly or have complex life cycles are more vulnerable than those with rapid reproduction and simple requirements. This selectivity means that the current extinction isn't just eliminating individual species, it's systematically dismantling the complex ecological relationships that have evolved over millions of years. Predator-prey relationships, pollination networks, seed dispersal systems, and nutrient cycling processes are being disrupted as key species disappear. The result is ecosystem collapse on a scale not seen since the worst mass extinctions in Earth's history. Coral reefs, which support more marine biodiversity than any other ocean ecosystem, are being eliminated by warming temperatures, acidification, and pollution. Tropical rainforests, the most diverse terrestrial ecosystems, are being converted to agriculture and urban development. Arctic ecosystems are being transformed by rapid warming and ice loss. But here's what makes the current extinction crisis different from all the previous ones. For the first time in Earth's history, one species is aware of what it's doing and has the ability to change course. Previous mass extinctions were caused by forces beyond the control of any living organism. Volcanic eruptions, asteroid impacts, and climate changes happened regardless of how individual species responded. The current extinction is being caused by human activities that are, in principle, under human control. We know that greenhouse gas emissions cause climate change. We know that habitat destruction eliminates species. We know that overfishing collapses marine ecosystems. We have the scientific knowledge and, increasingly, the technology to reduce these impacts. The question is whether humans will choose to act on this knowledge before the extinction crisis becomes irreversible. Some changes are already irreversible. The species that have gone extinct in the past few centuries will never return. But many threatened species could still be saved, and ecosystem collapse could still be prevented if human societies chose to prioritize conservation over short-term economic gains. There are some encouraging signs. Protected areas have been established to preserve critical habitats. International agreements have been signed to address climate change and biodiversity loss. Some species have been saved from extinction through active conservation efforts. Renewable energy technologies are beginning to reduce dependence on fossil fuels. But these efforts are still small compared to the scale of the crisis. Human populations continue to grow, consumption continues to increase, and the rate of habitat destruction and species loss remains far above sustainable levels. The window for preventing mass extinction is closing rapidly. The story of extinction over the past 4 billion years reveals a consistent pattern. Mass extinctions eliminate most existing species but create opportunities for evolutionary innovation. The survivors of each crisis have generally been more complex, more adaptable, or more efficient than their predecessors. Life has not just recovered from mass extinctions, it has emerged stronger and more diverse. But there's no guarantee that this pattern will continue. The current extinction is different from all previous ones because it's being caused by a single species that has become so successful that it's consuming the biological resources that support all other life. If humans eliminate too much biodiversity, there may not be enough surviving species to support ecosystem recovery after the crisis ends. We are living through the sixth mass extinction in Earth's history, but we are also the first species with the knowledge and ability to prevent it. The choice of whether to continue the 4 billion year story of life's resilience or to bring it to an end rests entirely with us. The 99% of species that have gone extinct throughout Earth's history are not just casualties of natural disasters or evolutionary failures. They are the foundation on which all current life, including human civilization, is built. Each extinct species contributed to the evolutionary processes that created the complex ecosystems we depend on for survival. Every breath you take contains oxygen, produced by photosynthetic organisms that evolved after the Great Oxidation Event. Every bite of food you eat comes from agricultural systems that depend on soil formed by millions of years of ecological processes. Every medicine that saves human lives is based on chemical compounds originally evolved by other species. We are not separate from the extinction crisis. We are part of it. Our survival depends on maintaining the biodiversity that 4 billion years of evolution has created. The same intelligence and adaptability that made humans successful enough to cause a mass extinction may also be the tools needed to prevent it. The question is no longer whether we can survive mass extinction. Humans are probably resilient enough to persist through almost any ecological collapse. The question is what kind of world we want to leave for future generations, one that maintains the incredible diversity of life that took 4 billion years to evolve, or one where humans are alone on a planet of their own making. The story of extinction is the story of life itself, and the next chapter of that story is entirely up to us.